Hello everyone, myself Dr. NCH Ramgopal, working as Associate Professor in Mathematics in the Department of Humanities and Sciences, MLR Institute of Technology, Hyderabad. I welcome you all to today's session on functions of complex variables. In the course Vector Calculus and Complex Analysis, the Unit 1 is the vector integrals and vector integral theorems, which we have covered in the previous sessions. Now, from Unit 2, we deal with functions of complex variables. That comes under complex analysis. Now, my today's topic is functions of complex variables. And today, I am going to introduce what is a complex variable and what are the functions of complex variables and other related things. Then, the applications of complex variables and also the topics of Unit 2. The topics of Unit 2 and some definitions like limit and continuity. Now, coming to a complex number, we know that, for example, if I write 2 or 3 or any other number, all these are real numbers. And when we use I, that means if we introduce this I, that comes under complex number. For example, we know that root 4 is plus or minus 2. Whereas, to find root over minus 4, to find this, we write this minus 1 as I square and 4 as 2 square. So, which is 2I whole square under root. So, which is plus or minus 2i. So, we introduce this I in the case of square root of a negative value. And now, 2, 3, 4, all these are real numbers which are constants. For example, if I write x, y, some t, etc., these are variables, real variables. Since there is no I, these comes under real variables. In complex analysis, first we need to introduce what is a complex number. Any number of the form a plus ib or a minus ib, a plus or minus ib we can consider. For example, 2 plus 3i, 4 minus I, 1 plus 3i and so on. So here in this a plus ib, this a is called the real part and b is called the imaginary part. Since I is present, this b is called the imaginary part, but not bi. So, a is the real part and b is the imaginary part. So, for example, 2 plus 3i, this 2 is the real part and 3 is the imaginary part. For example, if I have written only 2i, that means 2i is in the form of 0 plus 2i. So, with real part 0. So, a complex number with real part 0 is called purely an imaginary number. There is only I. There is no real part, only imaginary part. Similarly, for example, if I consider 2, it's a real number. All real numbers are complex numbers with imaginary part 0. I can write this 2 as 2 plus 0 into I. So, that's why the set of real numbers is a subset of set of complex numbers. The set of real numbers is a subset of complex numbers. So, here we deal with such complex numbers, and similar to the real and imaginary part that we have discussed just now, 2 is a constant whereas x is a variable. So, here also 2 plus 3i is a complex number, whereas if I write x plus iy, this is called a complex variable where x and y are real variables. So, a complex variable will be in the form x plus iy, and we denote, in general, we denote a complex variable using z. If x and y are constants, then this becomes a complex number. So a complex variable is denoted by Z, which is in the form x plus iy. Now the introduction part, complex variables. The complex analysis is a branch of mathematics dealing with complex numbers and functions of complex variables. Just now we discussed a complex number is in the form of 2 plus 3i or a plus ib, and functions of complex variables. Complex variable means x plus iy or x1 plus iy1. So a function of such complex variable. Complex analysis deals with complex numbers or complex variables or functions of complex variables. And also it has several important applications in science and engineering. And complex analysis provides powerful tools that simplify calculations and enhance understanding in various engineering disciplines. So that's why complex analysis is a powerful tool in understanding various engineering concepts also. And its ability to model and solve real-world problems makes it an essential part of engineering toolkit. So this is another important point. Since using complex variables we can understand the various engineering concepts, and also we can analyze the actual concept. So this particular concept of complex analysis is an essential part of engineering toolkit. Now coming to the applications of complex variables. The complex variables can be applicable in many fields like science and engineering, particularly in engineering, electrical engineering. While dealing with AC circuit analysis, complex numbers simplify the analysis of alternating current circuits, that means AC circuits. In that, engineers use phasors, which are the complex numbers representing sinusoidal functions, to analyze voltages, currents, and making calculations easier. And also in signal processing, the techniques such as Fourier transforms. In Fourier transforms, we use the complex exponentials. That means e power I, complex exponential. This is the exponential form e power I theta, e power. So if we expand this, cos theta plus I sin theta. So again, this will be included sin theta and cos theta. The terms such as sin theta and cos theta also. So the techniques such as Fourier transforms are fundamental in analyzing the processing signals. Not only that, in fluid dynamics also we use these complex variables, particularly in potential fluid theory. In fluid mechanics, complex potential functions are used to solve problems related to incompressible flow and irrotational flow, etc. So this allows for the analysis of flow patterns around objects. Sometimes the flow will be, there is a flow, and here we have a sphere, and how the flow, the pattern of the flow. For example, there is a flow and there is a rectangular plate in that flow. Then in dealing with the pattern of the flow, the complex variables plays an important role. And also in vibration analysis. So model analysis, complex numbers helps us to represent oscillatory motions in mechanical systems. And also the complex exponentials simplify the analysis of vibrations and the dynamic responses. So again here we use complex exponentials. So as an engineering toolkit, this complex analysis helps a lot in understanding and solving various engineering problems. And coming to electromagnetics, in Maxwell equations, the solutions to Maxwell equations which govern electromagnetic fields often use complex analysis. Complex analysis techniques such as the method of complex potentials are employed in electromagnetic field theory. So here in electromagnetic field theory and also in solution of Maxwell equations, we use the complex analysis. And in heat transfer also, this complex analysis plays an important role. So here, particularly the concept of conformal mapping. So this comes in the last unit of this particular course, conformal mapping. This topic allows engineers to transform complex geometries into simpler ones. So when a complicated problem is reduced to a simpler form, then it is very easy to solve such problem. Hence, complex variables or functions of complex variables or the complete complex analysis is helpful in solving many engineering problems. Now, coming to the topics that we are going to discuss in Unit 2. The Unit 2 is functions of complex variables. Here, we deal with complex variables, the introduction to complex variables, and then the main limit and continuity, limit of a complex function, and analytic function, harmonic function, Milne-Thomson method. And this is a particular method when the real part is given to find the imaginary part of an analytic function. And also, if imaginary is given to find the real part of an analytic function, we apply this Milne-Thomson method. Now, coming to the definition of function of complex variable. A function of a complex variable. Here, just now I told you, the complex variable is denoted by z, which is x plus iy. Now, function of a complex variable means f of z. The result will be some other complex variable that is denoted by w. So, this is the notation. W equal to f of z is generally expressed as a mapping of transformation from a complex plane z to complex plane w. So, every z is mapped with a complex variable in w plane. That is depicted by this graph. Here, this is the z plane, and here, this is the z plane, and this is the w plane. For example, if you consider a complex variable z, it is mapped with another complex variable w in w plane. So, here x, y axis, and here u, v. That means after transforming, here we can write this in the form of u plus iv, again a complex variable. So, in the original complex variable we have x and y, the real parts, whereas after transforming into w plane, u plus iv, so u and v are the real and imaginary parts. So, the graph of this function often reveals properties of real valued functions of a real variable, because here we have the real variables x and y. They are transformed into u and v in the complex plane. Now, for example, z is x plus iy, so which is a complex variable. Now, a function of complex variable means f of z. This result will be another complex variable which is written in the form of u plus iv. And again here u and v are functions of x and y. So, u is a function of x comma y and v is another function of x comma y. So, this is the notation that we use in functions of complex variables. After, for example, f of z is z square. Then write w in the form of a complex variable. So, here what is z? X plus iy. Now, z square means x plus iy whole square, a plus b whole square, a square plus b square plus 2ab, x into iy. So, here x square, I square is minus 1. So, here we get minus y square plus 2ixy. So, this can be written in the form x square minus y square plus I into 2xy. So, I can denote this by u. So, u is x square minus y square and v is 2xy. Hence, w equal to f of z, which is z square, can be written as u plus iv, where u is this function and v is this function. U is x square minus y square and v is 2xy. Next, limit and continuity. Now, the definition of limit of a function f of z. this is a generalization of limit of a real valued function also. For example, if we have f of x, the limit extends to infinity, f of x is equal to L. The same notation, the similar definition that we use here. Let us consider a complex function f of z is said to tend to limit L as z approaches a point z0. If for every epsilon we can find a positive delta, epsilon means a smallest positive number, and for every epsilon there exists delta such that the difference between here, what we are using here, the limit of this function f of z is capital L. So the difference between f of z and L is less than epsilon. Epsilon itself is a positive, very smallest positive number, and the difference between these two is less than that smallest number. What does it mean? F of z is approaching L. So that is denoted by limit as z tends to z0, f of z is equal to L. And for a function, if limit exists, that must be unique. So if you are getting different values, that means it's the limit doesn't exist. So limit, if exists, should be unique. And continuity. A function f of z is said to be continuous at the point z equal to z0 if f of z0 must be defined, and also the limit as z tends to z0 f of z is equal to the value of f of z0. So we have the function f of z, and as z reaches z0, we are finding the limit of this function. As z reaches z0, f of z should reach f of z0. Then the function is said to be continuous. And there are some properties like f of z is said to be continuous in a domain if it is continuous at every point of the domain. For example, if you consider a domain capital D having several complex variables, at each and every point of the z, if it is continuous, then the function is said to be continuous in the domain D. And if f is continuous, then it is bounded to. That means the upper and lower bounds exist. If f and g are two continuous functions which are continuous at z0, then f plus g is also continuous, f minus g is also continuous, product of these two functions is also continuous, and f by g or g by f are also continuous if the denominator function is not equal to 0. If the denominator is 0, that tends to infinity. And also mod f of z is also continuous, and continuous function of a continuous function is again continuous. So these are some properties of continuous nature. And in today's session, I have introduced what is a complex variable and what are the functions, how to denote the functions of complex variable, and the topics that we are going to discuss in Unit 2, the functions of complex variables, and limit and continuity of a function of complex variable, and some applications of complex variables in science and engineering fields. So in the next session, we continue the topic of limit and continuity, and then we switch over to the next concept of analytic function. This is for today's session, and we will meet in the next session. Thank you.